Good afternoon, everybody. Welcome to Coffee with Caleffi this month. My name is Cody Mack. I am part of the Caleffi team. And Bob Hot Rod Rohrer is not going to be here this month. He is off shaping mines. I believe he was in Nebraska, if I remember correctly. So this month's webinar is going to be on combustion theory and concepts for hydronic systems. It's going to be part one of a two-part series. Make sure to check in next month as the webinar will be about designing systems around condensing boilers. Our speaker for this month is going to be our engineering training manager, Jody Samuell, a very well-seasoned individual in this particular subject with most recent work experience at companies like Amtrol and most notably Wiesmann. And I think it's going to be a great webinar. We hand things over to Jody.
Welcome. This is Jody Samuell. Today's topic is about combustion with hydronic systems. Now, as people probably look through the hydronics, you're going to notice that there's not a reference there because usually we'll start off with that reference piece. Now, when we talk about hydronics and we talk about efficiency, everybody tends to look at it from a system standpoint. I always did. Now, the reality of designing for efficiency is systems will go in, they'll be designed for efficiency, centered around a condensing boiler, and when the job is installed and people look at the performance, the question always comes up about, is it performing to the expectations of the building owner, be it a homeowner or be it a commercial building? And whenever I've been involved in those discussions, everybody always tends to start at different points to look at the problems or the shortcomings. Now, for me, having worked for a couple of boiler companies, my first thought was always, let's start at the beginning and let's work our way out from the boiler. Because from an efficiency standpoint, the system can only be as good as I am at converting the energy into the fuel, from the fuel into thermal energy that I can utilize within the boiler. So, that's really kind of the focus of our discussion today. Now, first off, I want to thank a few people that helped me along the way. Not working, since Caleffi's not a boiler company, I was able to call on friends through the industry to get information to add to the presentation or just discussion. And these gentlemen all helped me along the way. Steve and David of Wiesmann US, Mike McDonald of Peerless Boilers, Evan Levesque of Dan Davis Sales. Not only is he Caleffi's rep, but he's also the Carlin Combustion rep. Bruce Fall of Shamrock Sales, he's also the Lochinvar rep. I've known Bruce for a long period of time. And last but not least, J.P. Rivet of Wiesmann US. They'll probably hate me for saying this, but among the people that I know in the industry, he's probably among the boiler gurus out there within the industry. So, what are we going to talk about? Kind of took everything I was looking at and tried to boil it down to 4 points. When I started this, like most of these, had a lot of information. And then all of a sudden I said, what, let's talk to somebody. I happened to bounce a couple of emails over to Roy Culver, and he's like, how many hours are you taking to do this? And kind of confirmed what I knew. I had way too much, bit off a way too large of a chunk of information to really cover into the time frame. So this is what we're going to look at. We're going to look at the combustion process. We're going to talk about excess air in the combustion process. We're going to talk about measurement, and then we're going to talk about efficiency. And as Cody said, next month I will be doing a presentation on condensing boiler efficiency. So for me, this really is that first step in that if you don't have a handle on combustion, it's hard really to take a look at efficiency from that condensing boiler side of things. So let's start talking about fire, combustion. It says the circle of combustion. Other people will call it the triangle of combustion. But to have combustion happen, I need 3 things. I need fuel, I need air, and I need a source of ignition. I have to start the process off. Now, in my little slide that I've gotten from Carlin, you see added that match in the center there. Not realistic when we're talking about combustion with boilers. Okay. So it's all about ignition to start that process off. Now, the fuel will only burn or react with oxygen if it's above the ignition temperature. Now, in the industry, I think I'm seeing more and more everybody is moving towards, if they're not there already, with the electronic spark ignition. And the nice thing about an electronic spark is I'm looking at a spark with a temperature of about 3,000 degrees Fahrenheit. with that kind of temperature, whether I'm talking about natural gas, I'm talking about propane, or I'm talking about oil, that electric spark is hot enough to start any of those fuels in their combustion process. Now, I'm mentioning about combustion. Once combustion is achieved, the ignition from the temperature from that burning process will provide the ignition source to continue to sustain that process. So I start off with ignition. Now I have to look at the conversion of my fuel to energy. So for most of my discussions, I'm going to probably center mostly on natural gas because it's a small molecule and it's a lot easier to work with than some of the other molecules and the other fuels. Now, when we talk about natural gas is mostly methane, CH4, 1 carbon, 4 hydrogens. So in the combustion process, I said I needed air, I said I needed fuel. From the air, I need the oxygen. So if I'm looking at 1 molecule of methane, I need 2 molecules of oxygen for perfect combustion. My combustion products become carbon dioxide and water vapor. 1 molecule of carbon dioxide, 2 molecules of water vapor. Okay. Now, when I start to look at actual combustion in a boiler, I'm not bringing oxygen, a source of oxygen in there, direct oxygen. I'm using air as my source of combustion. So that has to be considered when we talk about setup of the boiler from a combustion standpoint. Because the air is about, I'll call it 21% oxygen and about 79% nitrogen. You will find those numbers change as you talk to people, and a lot of that's about 1% of air that's actually trace gases. Most people round it up to the 2 gases. So when I look at that combustion process, it's not just about oxygen and air, it's about oxygen, nitrogen, and my fuel. Okay. How much air do I need? It's really about the size of the molecule of the fuel. How many bonds are there? How many carbons are there? So if I look at methane, methane consists of 1 carbon and 4 hydrogen. I move on to propane, 3 carbons and 8 hydrogens. The more hydrogen, the more carbon, the higher the heat value. The higher the heat value, the higher the calorific value is as well. Also, when I burn this fuel, the more carbon and the more hydrogen the fuel has, the more air I need to support that combustion. So let's look at that from the aspect of natural gas. We'll go again, stay with methane, and air. My air consists of nitrogen and it consists of oxygen. From that air, all I'm going to be utilizing effectively is the oxygen, and the nitrogen is going to just essentially pass through the process. So I have 1 molecule of natural gas, I have 2 molecules of oxygen, I pass it through combustion, I get 1 carbon dioxide and 2 water vapors. The nitrogens balance on either side. They're passing through the combustion chamber and the boiler during this process. If I move up to propane, C3H8, now I don't need 2 molecules of oxygen to support complete combustion. I need 5. So to get 5 molecules of oxygen, I need more air. And from a product standpoint, I've moved from 1 carbon dioxide to now 3. I've moved from 2 water vapor molecules to 4. So you'll find that with each different fuel source, there's going to be a different requirement for air, and there's also going to be a different mixture of the combustion gases. Now, let's talk a little bit about that nitrogen. Okay? I'm going to use the term it's along for the ride. It doesn't participate in the combustion process. So the nitrogen comes in as part of the makeup air. That makeup air could come from the boiler room, or it could come from outside air, depending on how things are set up. So it enters the combustion process at ambient temperature. Could be the ambient temperature of the boiler room, could be outside ambient temperature. Now, when it exits at the exhaust temperature. Okay? The nitrogen is part of what's referred to as the stack losses. The heat from combustion that ends up going up the vent or the chimney of the boiler. So when I start to look at being efficient in the combustion process, one of the things I have to consider is how do I minimize the amount of the energy from my combustion process that's going up the stack. Part of it is addressing how much air or nitrogen is passing through that process. A lot of information on this chart. I'm going to go right down to the middle of the block I just looped off in blue. The combustion ratio. Okay? What this combustion ratio is it's looking at the combustion process. You know? I need a certain amount of oxygen to completely combine with my fuel to provide essentially carbon dioxide and water vapor. So if I'm doing natural gas, my combustion ratio is 10. I need 10 cubic feet of air to burn 1 cubic foot of natural gas. In that process, when it's finished, all of the carbon will be converted to carbon dioxide. All of the hydrogen will be converted to water vapor. If I'm doing propane, the combustion ratio is 24. I need 24 cubic feet of air to support the combustion of 1 cubic foot of propane. And again, this is perfect combustion where I have the exact amount of oxygen to support complete combustion of my fuel. I'm going to throw another term in, excess air. This is one that we'll be utilizing through our discussion. And as we talk further, excess air is actually going to be described in terms of a percentage. But for right now, I want to say when I look at combustion, excess air is any air more than prescribed by the combustion ratio. So if I'm burning propane, I'll go natural gas, and I need 10 cubic feet of air to burn 1 cubic foot of natural gas, if I'm bringing in 11 cubic feet of air, I have 1 cubic foot of excess air. That excess air is not needed. That 1 cubic foot is not needed to support the combustion process. It's like the nitrogen that we talked about earlier passing through the boiler and carrying heat out with it as it exhausts the boiler. So take a look at it from an aspect of molecules. So originally when I looked at natural gas, I had 2 molecules of oxygen. Let's double the air. I double the air, I've doubled the number of oxygen. So I have 4 molecules of oxygen. I still only have 1 molecule of natural gas. So I'm only going to utilize 2 of those molecules in the combustion process. I still end up with 1 molecule of carbon dioxide. I still end up with 2 molecules of water vapor. But now what shows up in my combustion gases is now oxygen molecules. The oxygen that came in with the air that was more than I needed for perfect combustion, it doesn't get consumed or combined in the combustion process. It shows up in exhaust gas as oxygen. Now, from this drawing, that block that I just blocked out that's gray and blue, that's my excess air. So when I look at stack losses and having energy leave the boiler and go up the chimney, I have many more molecules exiting, carrying heat away than I did when I was at my perfect combustion balance between air and natural gas. So one of the first things we need to discuss is if excess air is going to rob energy from the combustion process, and I'd like to be able to control that process to have efficiency, I need to have a way to measure and determine and adjust the combustion process from the aspect of air and gas to maintain good, clean combustion at a good level. So I really need, if you will, markers that I can use to measure and adjust. A couple of things to look at. Let's look at our combustion products, carbon dioxide and water vapor. When I look at a firing rate, I look at how much fuel I'm burning. For a set amount of fuel, I'm always going to get a set amount of carbon dioxide. I'm going to get a set amount of water vapor. And when I look at this, I'm going to go to CO2. It's something that I can measure. So I can measure the carbon dioxide in my fuel gases to take a look at how my combustion process is working. In simple numbers, simple terms, if I have perfect combustion, my carbon dioxide should be at the highest. It's the largest, it's showing its largest percentage of my combustion gases. As I add excess air, I end up with more molecules in my exhaust. All of a sudden, that fixed volume of carbon dioxide now starts to drop. That's something I can use to determine how good my air to gas, my fuel to air ratio is. Now, on the other side, I have my molecules that show up in the flue gas whose concentration are variable based on the excess air itself, nitrogen and oxygen. Let's take a look at oxygen. As I increase the excess air, I'm still only utilizing a certain volume of oxygen to support the combustion process. So as excess air goes up, the amount of oxygen, the percentage of my flue gases that are oxygen, go up as well. So if I can measure the level of oxygen in my flue gas, I can then be able to measure and then control the combustion process. Now, Cody, do we have any questions that we want to answer at this point?
I was actually going to mention that, Jody. If anybody does have any questions, just make sure to write them in. We'll try to handle them as they do come in. However, we don't have any right now. If we don't get to your question during the broadcast today, we will be answering every single one of them via email or contacting you by phone. But at the moment, we're doing really good, Jody. Thank you.
Thank you. All right, so let's talk about measuring it. Okay. Combustion analyzers. Love this picture. This actually happens to be Roy Culver, with a combustion analyzer in hand, and I hate to say, I look at the look on his face, and I've been in mechanical rooms, and I've seen that face on contractors. Now, one of the big discussions that always happened when I'd work for boiler companies and we talked about combustion, it was always, well, what do you measure? Do you measure CO2 or do you measure O2? To me, they're the opposite sides of a coin. Now, one you're looking at a combustion gas, one you're looking at a portion of the excess air. For me, the important thing is just make sure you test. I'm amazed at the number of times out there where somebody will have a boiler and they will say it's not burning correctly. And somebody goes out there to help them set the boiler up and there's not a combustion analyzer to be found. With the equipment, if I'm looking to drive efficiency to where it needs to be, in order to set things up properly, I have to have the tools. So from the aspect of testing, could be CO2, could be O2. They're both going to get you to the same point. Now let's talk about test equipment. So really, there's two types of chemical testers out there. There's a chemical tester and an electronic tester. The chemical tester is a Baccarat pyrite tester. Most guys, will refer to this as a wet kit. It's a tester with fluid in the kit, and it will either measure O2 or CO2. So you choose which test kit you want to use. We also have electronic testers, and that's probably where everybody has been going because of the fact that it provides you with so much information. Let's take a look at the chemical testers. Okay. Kind of a sterile picture of this. This picture here happens to be J.P. Rivet's wet kit. And when I started to look at pictures and everything, I gave him a call and said, hey, you wouldn't happen to have one, a wet kit? And he's like, oh, yeah, but I haven't used it for about 1.5 years. But he still has it. Okay? So it's a full kit to get out there and test the boilers. So we have in here a draft gauge. We're going to kind of push that one to the side. But when I'm doing a chimney, it's important to have a draft gauge to make sure I have proper draft in my chimney. Over here, we have a thermometer. If I'm looking at efficiency, I need to know the incoming air temperature and the stack temperature to get a net stack. That's part of the efficiency calculation, important part of the kit. Here's my wet kit portion. We're going to come back to that in a second. And then I have an efficiency finder. Allows me to go in there with essentially a slide rule, and with the information I get from my wet kit to calculate the burner efficiency. Okay? So here's the wet kit, the Baccarat Pyrite. It's a chemical reaction. So it's either filled with a fluid that reacts with carbon dioxide or oxygen. Essentially, this is hooked to essentially a little hand pump. It's placed into the flue of the boiler that it's pumped. Once it's pumped, the fluid is mixed, and then on the scale you see it on the side, the level is red for the level of carbon dioxide or the level of O2, depending on what kit you have. The one thing with the cat, it is filled with a liquid, and that fluid doesn't have an endless life cycle. I think of it CO2. It's good for about 300 tests. If it's O2, it's about 100. So it does have to be replaced on a regular basis. But from an aspect of getting a reading for O2 or CO2, these work as well as any electronic tester. Now, I said there's a scale in there. You know, once the test is done, it's always good to not only look at the CO2 or the O2, but also the efficiency of the boiler. So I have a sliding scale with a little window where I will find the net stack. That's where the thermostat comes in handy. I need to measure the incoming air temperature, the exhaust temperature, subtract the incoming from the exhaust, and I have a net stack. So for instance, for this example, let's say the net stack is 400 degrees Fahrenheit. I then, with this moving scale, put the arrow on the CO2 level. For this example, we're going to say we're at 12.5%. I then look in the small window, and from the small window, and it's a little bit tough to see, it's telling me that the fire efficiency is 84%. Okay? A little bit old school, but just as effective as doing it with a combustion analyzer. That's the wet kit. This is where most people are going nowadays, electronic. So here's one version of it. Here's another version. The nice thing is I enter in my fuel type, and then I can read CO2, O2, carbon monoxide, excess air, NOx, efficiency, room temperature, stack temperature, and some of them have other things beyond that. So it's a quick and easy way of getting in there and reading this information. The one thing to remember, just like the wet kit, this is not good forever as far as the sensors within it, so it does have to be calibrated on a regular basis, and a couple of the sensors do have to be changed. The other thing I like about the electronic analyzers, this happens to be a Wohler one, is I have the ability to print out the results. So it's not where I sit there and hopefully I write it down or I just say it's good. I'm able to print it out, and you'll go into buildings where they have a 3-ring binder with all the printouts of the combustion analysis, or they may be stapled to a series of tags with wire wraps somewhere around the boiler, but it does give you that history of where the boiler was set up the last time somebody was there. So from our aspect, we have a combustion process. We have to be aware of the excess air passing through it, and there's a couple of testers out there, both the wet kit and the electronic style, that allow me to get in there and measure the carbon dioxide or the oxygen, which both are great indicators of how much excess air I'm flowing through my boiler. So the next thing becomes, well, if I know I can measure it and I know it's there, where do I want it to be? So we're going to talk first about perfect combustion. The long word, you see it on there, is stoichiometric combustion. That's combustion when I have my theoretical air-gas mixture. For natural gas, for instance, 10 parts air to 1 part natural gas. So if I look at CO2 under perfect conditions, my natural gas is going to be somewhere between 11.8 to 12.5. If my fuel is propane, under stoichiometric conditions, 13.6 to 13.8. And for fuel oil, 15.4 to 15.6. I should never see a reading higher than these. These are, again, the zero excess air number. Now, you'll notice there's a little bit of a range there. Okay? Now, when I look at my fuels, for instance, we started off talking about natural gas being mainly methane. Natural gas and propane and oil has usually a grouping of some different molecules. So, for instance, if I look at natural gas, methane is the main constituent of natural gas, but it may be as low as 85%. It may be high as 97%. Natural gas typically also has ethane as one of the components of it. It makes anywhere from 1.5 to 7%. And then propane anywhere from 0.1 to 1.5. So because of this mixture of gases within natural gas, that's why you end up with a band for perfect combustion. And it depends on the mixture. So if I'm doing natural gas, I'm going to shoot in the middle. If I have my combustion ratio right on, I had 10 cubic feet of air to support 1 cubic foot of natural gas. I put a combustion analyzer at the outlet of that boiler. I should see a CO2 in the range of about 12%. Okay? Now, we kind of talked about moving to the edge, where I'm adding extra air, and how it pulls energy. It increases the stack loss of my system. When I start to look at combustion, I also have to look at the other side. What happens if I don't have enough air? From a combustion standpoint, I'm still going to get combustion, but it's not going to be complete combustion. So if I'm short oxygen, rather than having two oxygen molecules per carbon molecule you see here, let's say I go to 1-to-1. All of a sudden, I don't have enough for carbon dioxide. I end up with carbon monoxide. Okay. Now, the important thing with carbon monoxide, if you see carbon monoxide, it's not always an indication that you don't have enough air. Okay. You could have carbon monoxide because you have too much air. Additionally, you can have carbon monoxide because there's insufficient heat within the combustion chamber, a cold combustion chamber. Let's take a look at that. So if I look at a cast iron boiler, here's a 3-phase cast iron boiler, drop the flame in the center of it, and I have a small blue circle around that flame. I'm referring to it as the outer envelope of the flame. Now I've also drawn an orange circle around the outside, the inner surfaces of the cast iron boiler. Now, where I tend to see the results of this chilled flame or this cold combustion chamber is on that outer surface of the flame itself, that outer envelope. And that if the cast iron is not hot enough, there's not enough reflected heat in that boiler, and even though you have enough oxygen available, the gases in that outer envelope just don't achieve complete combustion. This is also why when you talk to people about setting up boilers, cast iron boilers, they typically will say any numbers probably from as short as 5 to maybe 15 minutes of runtime on the burner before you even consider putting your combustion analyzer on the boiler itself. And one of the reasons why is they want the combustion chamber to heat up so that I don't have a chilled flame, so I don't get an erroneous reading of carbon monoxide. Why is it a concern? It's a health concern. Carbon monoxide at different levels can cause certain problems. I mean, as low as 50 ppm, that's maximum concentration for continuous exposure in any 8-hour period. So when we look at combustion, it becomes a balancing act. I want to make sure I have enough air so I don't have incomplete combustion, but I don't want to have too much air so it ruins the efficiency of my system. Cody, any questions to be answered at this point?
Well, to be honest with you, Jody, as soon as you started talking about combustion analyzers, I think you pushed a hot button. With that in mind, we had one question. Let me find it here. From Charles. He asked if nitrogen or N2 just passes through the combustion process, why do manufacturers advertise their boilers or burners as being low NOx?
Yes. So nitrogen oxide, NOx, usually as a nitrogen oxide, an NO, or nitrogen dioxide as an NOx. Normally, nitrogen and oxygen essentially coexist in air separate. However, if my flame is running exceptionally hot, a hot flame will provide sufficient temperature that you actually have the formation of NOx or NOx. So usually when somebody says they have a low NOx burner or a low NOx boiler, they've designed into the boiler something in the burner system, the burner itself, to drop the flame temperature down to control the NOx. Now, why NOx is a concern is NOx is a greenhouse gas. So there's many areas of the country. I think Washington State, I think California, I think Texas on the commercial side of things have very stringent standards for the controlling of NOx. Any others? We'll do probably one more, Cody, before we move on. If there's any else?
Yeah, just something to as a point of information. John actually mentioned that as far as wet kits, as far as being possibly obsolete at this point, I think you'd agree with me, they are still very functional, but what he mentioned was that it just provides a snapshot of the efficiency. It won't necessarily, I mean, unless you're constantly keeping up with it and everything like that, or constantly doing tests, you're not going to get an overall efficiency over a period of time like a combustion analyzer. I think you just wanted to kind of go over the history is what you were kind of thinking. Is that correct?
Right. Well, and that's a great point that you have there, and that it's with any combustion analyzer, it's only giving you, whether it's the wet kit or an electronic, it's only a snapshot of when that combustion analyzer is hooked up. You know, one of the things that always comes up when we start to look at boiler conversion, let's move from a cast iron boiler to a high efficiency. Okay? You know, all of a sudden you'll see the results of the combustion efficiency of the existing boiler that was taken probably after the boiler was cleaned, and because of the fact that somebody's trying to get their maintenance done, the boiler's not at 180 degrees, it's down around 90 degrees or 100 degrees, and because of the fact that the boiler is clean and the water temperature is cold, that drops the net stack down considerably, and the efficiency isn't normally achieved day in and day out. But you know, that is a great point, that we are looking at a snapshot rather than long-term operation on the equipment.
Yep, and another good point to mention is that some of the combustion analyzers now are offering data logging as part of their features, which is a great thing that you can just take straight to your computer, as opposed to, you know, a basic printout of, you know, a snapshot in time, like we mentioned previously. Nice feature there. So.
Yeah. So you know, a lot of these now are going to Bluetooth, where you can feed it directly into the computer to data log, and also to hold it in memory. Interesting point on wet kits, and Cody came on. When I put the picture up there, Cody's like, "What is that?" So you kind of look at this, and a lot of the younger generation has never seen the Baccarat wet kit combustion analyzer. So let's talk about excess air. So in the real world, when I start to look at the application, I want to make sure that I don't form carbon monoxide. It's not good for the system. Conversely, I don't want to have too much air, because then I start to lose energy out the vent. So the question becomes, where do I need to be? The reality is, because it's a dynamic system, I need to provide excess air to keep myself far away from going into incomplete combustion. On the oil side of things, if the oil temperature changes, the firing changes. If we have varying sources of supply of the fuel, if the heating value changes, the CO2 level will change. It happens with air temperature, its pressure, its furnace pressure. All of these things combine to say, you know what, in order to stay safe, I have to make sure I have a certain amount of excess air always going into my combustion process. round numbers, and I think most, you look at most manufacturers, they're probably in this range. Most of the time, everybody says, yeah, I probably want to be somewhere between 17 and 30% excess air for best performance. It gives me a great safety margin, and it also ensures that I'm not wasting too much energy increasing my stack losses. Now, since we typically look at CO2 or O2, let's convert those to CO2 or O2 numbers. Let's talk about why not going too high. We kind of already talked quite a bit through about the excess air. But the big thing is, as I put excess air through, I'm going to keep that nitrogen as it's passing through without adding to the combustion process. The more nitrogen, the higher the stack losses. Now, the other thing that also happens is, for a set input, if I increase my excess air, say from 30% to 60%, I'm going to see my combustion temperature drop. Because if I have a set number of BTUs of energy that are going into that combustion chamber, that flame, if I'm heating 50% more molecules, since that same heat is spread over a larger number of molecules, the combustion temperature drops, which can affect heat transfer. Since in the heat transfer process, and hot goes to cold, if my hot isn't as hot, I'm not going to see as high as heat transfer. So if I look at my 17 to 30% excess air, if I'm looking at it through the eyes of oxygen, I'm probably in that range of about 3 to 5%. For natural gas, ideally I'd like to be between 9.1 and 9.8. If I'm doing propane, somewhere between 10.7 and 11.1. And fuel oil, I'd like to be somewhere around 12.1 to 12.7. And that will get me into the, if you will, that sweet spot. I'm safe, but I'm not wasteful. Now, I thought a couple of slides here that Evan had sent me over from Carlin that I thought were real interesting. Okay. Now more and more boilers are now going to direct vent systems where the combustion air is coming in. The chart off to the left-hand side looks at the various air temperatures, the air density under those temperatures, and then if I was trying to achieve 19% excess air, which is about 12.8% CO2, that's the amount of air required to support combustion and achieve 19% excess air. So if my air temperature is 0 degrees Fahrenheit, which happens up here in Wisconsin, I happen to be up here this week, on a 0 degree day, I need 1,456 cubic feet of air to achieve 19% excess air. I take that same boiler on a 60 degree day, the air is less dense, the amount of air required goes up. It's now up to 1,646 cubic feet of air. So when I start to look at applications where I'm doing steel combustion, and I look at the combustion at that time, back to that comment, the great comment about the combustion analysis is a snapshot. If I have a boiler set up for 28% CO2, I mean a 12.8% CO2 on a 40 degree day, I will see a change in the CO2 level as the outside temperature changes. It's normal that way. It's not where I'm going to go in and every single day at 12.8. The CO2 is going to track changes in the outside temperature. Another way to look at it is tying it into, say I was looking for 12.8 on a 70 degree day. In order to achieve 12.8 on a 70 degree day, on a 10 degree day, I should be set up somewhere between 10.9 to 11.5. And if you look at those numbers actually show how the CO2 would track as the incoming air temperature changes. And so the one thing to remember with combustion is, I set it up today, and I'm going to actually back up here a bit. And if things change, the combustion process will change with it. But if I'm set up right for my excess air, I never will cross that line where I'm going to achieve incomplete combustion. Now to get back where I was. So, how does combustion affect efficiency? To realistically look at the efficiency, I have to look at two items. I have to look at excess air, and I have to look at stack temperature. And rather than looking at the little slide rule, this happens to be a great chart that ties together your excess air measured through CO2 or O2 and your net stack temperature. So we start on the bottom with CO2. Let's say I'm at 9.5% CO2. I come up to my CO2 line. It shows me I'm at 25%. I follow that all the way up. And let's say I have a net stack of 400 degrees. That's telling me my efficiency is about 80.5%. Now, you'll notice how the line slope down as we move to the right. Back to the whole concept of excess air increases my stack loss. So the higher the stack temperature, the higher the losses. The higher the excess air, the higher the loss. Okay? So that's why when we look at performance, and that's why I want to maintain that 17 to 30% excess air so I can stay in a good region when it comes to my combustion efficiency. Now, with this chart, this is sensible heat only. Right? It doesn't address the latent heat from my fuel, which with condensing boilers I'm concerned with. So if I look at combustion process and I start to think condensing boilers, it's about the water vapor. The two molecules of water vapor that are formed when I burn my natural gas, my methane. Okay? So those water vapor, that is at a fixed amount. Now, just as with carbon dioxide, that's at a fixed amount as well. So as I change my excess air, the percentage of my flue gas that is water vapor will change with it as well. Now, how much energy can I get? It depends on the fuel type. If I'm doing natural gas, about 10% of the energy is tied up in that water vapor. If I'm doing propane, it's about 8% of the energy. If I do number 2 fuel oil, it's about 6%. And what's interesting I like about this is it had the numbers on the other side as well. That 10%, that's about 93 pounds of water per million BTUs with natural gas. Propane, it drops down to 75. Fuel oil, it becomes 59. So when I look at doing a condensing boiler, my goal is to harvest this energy by dropping my temperatures down where it changes from a vapor to a liquid. Now, you talk to anybody and you say, fill in the blank, a condensing boiler will condense at blank water temperature. Usually the number that's thrown out is usually somewhere between maybe 130 or 135 degrees Fahrenheit. Now the reality of combustion is because that amount of water vapor is set, if I increase my excess air, it becomes a smaller percentage of the overall combustion gases. So I reduce the percentage, I've reduced the dew point. So if I look at setting up at 10% CO2, 10% CO2, my dew point's around 132 degrees Fahrenheit. If I'm down around 7% CO2, my dew point's around 118 degrees Fahrenheit. Okay. Why is that important? For a condensing boiler to condense, the return water temperature has to be lower than this dew point. So if I run more excess air, I've suppressed that dew point. All of a sudden, a boiler that should be condensing with a return water temperature of 128 degrees is now not condensing until it has a return water temperature of 118. The boiler spends less time in the condensing mode. The other thing that happens is when it is in the condensing mode, because of the positioning of the dew point, I get less condensate. If I'm at 10% CO2, I look at that condensate drain, return water temperature, I may see a trickle of water coming out of that. If I'm running at 7% CO2, it may just be a little dribble coming out. So from the aspect of condensing boiler performance, it's very important that I have the burner set up properly. Proper burn-up setup means a proper dew point for condensing, which will help from the performance aspect with that condensing boiler. We will talk more about this next month when we talk about condensing boilers, by the way. So far we've made it through. We've talked about combustion itself. We talked about the process. We've talked about the role of air in the process and the oxygen. And we've worked on the concept of excess air, what it is, what's good about it, what's bad about it. And then we looked at the measuring, the combustion analyzers, and then tied that back to how setup affects the efficiency of the system. Now there's the other considerations. And these are the ones that I always have, with Bruce Fall and J.P. Rivet. The phone calls that I'm thinking are going to last about 5 minutes and I'm on for a half an hour. Let's talk about some of these other considerations. In certain parts of our market, oil is still a viable fuel. In fact, with some of the oil prices I've seen over the past couple of months, it seems to almost be making a comeback. Now, we always talk about the fire triangle or the fire circle as what's needed to achieve combustion. Okay? The other thing that has to happen is the fuel has to be in a condition that it will burn. Okay? Oil in itself, number 2 heating oil, doesn't burn readily by itself. It needs to be put into a form that it will burn. That's the purpose of the nozzle. Okay, the oil will come in. Nozzles are typically sized. If you see that stamping on the size of 0.75, that nozzle will be able to pass through 0.75 gallons per hour of number 2 heating oil at 100 psi. Now, in order to burn that, I have to atomize or vaporize it. So it passes through, and the other thing the nozzle does is it vaporizes it. The nozzle will have a pattern. It may be 45 degrees. It may be 60 degrees. It may be hollow. It may be solid. But that pattern and everything will set it up so that the fuel will burn. And if I'm doing it right, I get a lot of droplets. It's a very big number, but I atomize it. I get it into essentially a volatile vapor. The oil will now burn. I've run across guys that have had trouble with combustion, gone in there, put my pressure gauges on, and found that they cranked it down to about 60 psi. At 60 psi, it's not coming out and atomizing properly to allow it to burn. So this is very important when we start to look at burning oil. The other thing also, a little side note on this, follow the manufacturer's recommendations for the nozzles. Anytime I tend to see a little bit of a problem, a lot of times somebody will deviate from what the manufacturer is looking for in nozzles or in pump pressure. The other thing that's required is turbulence. Okay, I need to mix my air and my gas to get that combustion. I'm going to jump down to the premix burner on the bottom. It's real easy. The blue is my combustion air. The yellow is my gas. It's drawn in at the suction side of the blower. The movement of the wheel in the blower will mix the gas, providing a good air-gas mixture that will give myself a nice clean combustion. When I do I'm going to call it a gun-style burner. You can see that flame on the top there. The turbulence is provided by the slots in the head. The air passes through, and those slots will generate that turbulence. Now, one of the questions always comes up when I'm dealing with people on the oil side of things, and they say, Jody, I have a head setting and I have an air gauge setting. Which one do I adjust? My answer always is both. So I put on there a P1, a P2, pressure 1 and pressure 2. In order to get that swirling or that turbulence on the head, I have to have the right pressure behind the head to get the right swirl pattern. So if I don't have enough pressure, I don't have good turbulence, and I don't have that good mixing. If I have too high of a pressure behind it, and also the turbulence may not be where I need it to be. So when I start to look at doing a gun-type burner, it's always a matter of let's adjust both. I think my final thing is to address going to high altitude. You know, whenever you start to talk about boilers in high altitudes, the first thing that always comes up is, how much do I have to derate my boiler? I got Dalton's law of partial pressures at the top. We'll actually talk about that later. But the reality is, as I start to work my way up to a higher altitude, the pressure and the density of the air changes. At my home in Rhode Island, we're pretty much at sea level. My atmospheric pressure is 14.7 psi. My air density is 0.075 pounds per cubic feet. I get all the way up to 10,000 feet, the pressure drops, the density drops. So according to Dalton's law of partial pressure, and I kind of boil it down to what I'm looking for, is the constituents will stay the constituents of the partial pressure will stay consistent. So, you know, when I drop the pressure, the nitrogen stays at the same point, the oxygen stays at the same point. And what happens is, when I start to go up to altitude per cubic feet of air, because the pressure is dropping, the amount of molecules drop, and so the amount of combustion that it can support drops as well. Now, you'll find that for boiler manufacturers, the numbers tend to be all over the place. But each manufacturer will specify how much the boiler has to be derated as the elevation goes higher due to this drop in density. Now, most of the manufacturers will run off of a number somewhere between 2% and 4% of the capacity reduction for each 1,000 feet of elevation. This here actually ended up, after a discussion with JP Rivet, ended up throwing this in. Yeah, so you look at this, and they actually have an adjustment at 5,000 feet. So from 1,000 feet to, from sea level to 1,000 feet, the boiler is derated at the rate of 3%. At 5,000 feet, they have a change that's made. The boiler goes back up to 100%, and then it's derated from 5,000 feet to 10,000 feet at 1.6% per 1,000 feet. You know, but the end result is, when I look at the boilers, I look at them at altitude, I have to consider the altitude to make sure that I'm selecting the right boiler, that the combustion gases will, the oxygen in the atmosphere will support the combustion within that boiler. So, a lot of ground covered today. You know, we talked about system efficiency, and from a system efficiency standpoint, it's really built on combustion, and we'll talk more about system efficiency next month in my condensing boiler class. Again, excess air is required, and it's fuel and application specific. Right? We talked about why we need the excess air. As important as anything else, proper combustion needs to be verified, and I need to use the right tools. And finally, I'm going to ensure the boiler manufacturer's recommendations are met for proper setup. The manufacturer will tell you what should happen with that boiler to get it set up and running properly.
I wanted to thank you, Jody, for your time. I think we hit a lot of good topics here and a lot of good information to help people understand just the very beginnings of combustion. And again, thank you everybody for your time, and enjoy the rest of your day.